All right, so let's start talking about motion. So I already mentioned just a second ago that if I'm looking at position, I'm defining a starting point. And if I'm on a number line, my starting point could be 0. My starting point could be 1. My starting point could be 2. I'm just defining a starting point. So it's just like what we're saying, that we're looking at how things are going before. So here's a -1, here's a -2, here's a -3. So if I have a little car and I've got my starting point at 0, and I'm going to move to a new starting point, I'm looking at a change in position. And my change in position, we're defining as displacement. And we typically represent it as a change in X. Now, it could be a change in Y. It could be a change in Z. It could be a change anywhere we're dealing with, but we're starting with one-dimensional motion, and it's easy to think of in the XY direction. Now, displacement is an interesting concept. So if I'm at my starting point, I can represent that as X sub 0, or I can represent that as X sub I. Initial point, origin, however you want to look at that. In physics, we use a lot of subscripts in order to be able to have what we're anticipating. So I have a change in position and displacement. Now let's think about that. Let's have a swimmer. My swimmer is going to be in a 50-meter pool. So this is a 50-meter pool. We start, the swimmer goes to one end, and swimmer comes back. Distance traveled is not equal to displacement. Because my swimmer swam 100 meters. But my displacement was my X sub 0 is equal to 0 meters. My X final is equal to 0 meters. My change in position, my change in X is my X final minus my X initial. So I have 0 minus 0 is equal to 0. So my displacement's 0, but my distance traveled is 100 meters. So when and the confusing thing that we have in physics is we're going to use that verbiage a lot, because speed, first of all, it's not a vector. It's not a vector, but it's equal to the distance traveled divided by my change in time. So I'm going to be in meters per second. So speed is in meters per second, but this is not a vector. This has only got a magnitude associated with it, and it is not the same thing as velocity. Velocity is defined as a change in position divided by a change in time. So that's velocity. Velocity is a vector. So it has direction and magnitude. It'll have units of meters per second. And we can look at it in a couple of different ways. One of the things that we can do is we can do a plot of position versus time. So if I do a plot of position versus time, we're going to give ourselves a scale here. Now, since I do open note, open resource, if you are given a set of data, and we're going to give ourselves a set of data, we're going to give ourselves position, and we're going to give ourselves time. So my initial position at 0 meters, I'm at 0 seconds. At 1 meter, I'm at 1 second. At 2 meters, I'm at 2 seconds. 3 meters, I'm at 3 seconds. 4 meters, I'm at 4 seconds. If I give you a table on a test and ask you to give me a position versus time plot, and it's open book, open resource, I'm expecting you to not just sketch it out on a piece of paper. I would like for you to go ahead and use Excel or Google Sheets or use a piece of graph paper. And you can download graph paper from the internet, but I'm really wanting you to actually utilize the resources that you have. So we've got our graph. And as you might expect, I've got a nice straight line. So I'm going to use my nice ruler, and I got a nice straight line here. Now, if I have a straight line, it's going to tell me something. This tells me if it's straight. One thing I know is that I have a constant velocity. I've got a constant velocity, and I can determine that velocity by looking at, and this is going to be in meters, and this is in seconds. I can calculate the slope of this. So there's my change in time. My change in time is equal to 2 seconds. My change in position is equal to 2 meters. The slope of my line is equal to my rise over run. This gives me my change in position. This gives me my change in time. And now I've got 2 meters divided by 2 seconds. This tells me my slope is 1 meter per second. So the magnitude of my velocity in this case is equal to 1 meter per second. So I can get that from my data to be able to get there. Now, I can also do, this can also be considered an average velocity, because I'm looking at my start and my stop. But we all know that, hey, we can have something called an instantaneous velocity. And that instantaneous velocity is what we call a limit as time is approaching 0 of my change in position over my change in time. And I think we discussed it a little bit on Thursday of last week, that I'm looking at a slope. So you're going to have a homework problem that's going to be something like this. I'm given a position is equal to 3.0 t cubed minus 10 t is equal or plus 3. And we want to look at the instantaneous velocity over the period of change in time, where time is equal to 4 seconds and the new time is equal to 5 seconds. So what you'll do for that one is you'll do X, and you're going to go in here and do 5 seconds. So I'm going to calculate what that X is. So I'm going to have 3 times 25 minus 50 plus 3 gives me a value of 28. I'm going to calculate X at 4 seconds. Okay. So I've got 4 squared times 3 minus 40 plus 3 gives me 11. So my instantaneous velocity is going to be my final velocity of 28 meters per, or my final position of 28 meters minus 11 meters divided by 5 seconds minus 4 seconds gives me 17 meters per second. But now we're going to do the exact same thing, except my change in time is going to be 4.75 seconds. And my new one is going to be 5 seconds. So I've already got my 5, so that's good. But I got to do my X at 4.75. So this is going to be 4.75 squared minus 10 times 4.75 plus 3 minus 47.5 plus 3 gives me a number of 23.1875. So now if I do my instantaneous velocity, this is 5 minus 4.75 seconds. And I have 28 minus 23.1875. There's meters. And I'm going to end up with 4.8125 meters divided by 0.25 seconds. And this gives me a value that's a little different. 19.25 meters per second. So we're getting an instantaneous velocity that's a little bit different. And then we'll show you a graph of that here in just a second. Okay, I'm going to actually do that. I'm going to stop sharing. Hopefully I don't get everything totally messed up. All right, so I'm going to share my screen again. All right, so I've got my Excel spreadsheet here, and I'm going to show you a couple of fun things. So first of all, we're going to write my equation. Now, what I'm going to do here, oops, go away. I'm going to put in a quotation mark or an apostrophe there, and I'm going to put in my equation so that we can all see my equation. I'm going to do 3t, and I'm going to put in my little caret so that we can all see that that's squared, minus 10t plus 3. So that's the equation we're going to do. I'm going to go ahead and give myself a position. And this is going to be my X, and it's going to be in meters. So I'm going to give myself my units. And the reason I'm putting position in front is because we're going to have time. So here's time. And this is going to be in seconds. And so I'm going to do 0, 1, 2, 3. We'll give ourselves, and you can do this a little bit differently. Now that we've got 1, 2, and 3 in there, you can do this little thing right here where you can actually put points. But now I'm going to put in my equation. So I'm going to say that this is equal to, and I'm going to go ahead and say 3 times that square times that square again, because that would give me my squared. You can do it that way. You can do it another way if you want, but I'm just going to try and make it easiest for us to see it. So I've got that times that square plus 3. And now I have an equation. And now I can copy this all the way down. I'm going to do control copy or control C. Oops. Copy, paste. Now I have my numbers, and we can go through and verify that that equation is correct. So we can actually see it. And now what I'm going to do is I'm going to plot it. So I'm going to come in here. I'm going to do an insert. I'm going to do a chart. I'm going to do a scatter plot. And now you can see that strange behavior here. But what that instantaneous velocity is doing, I got that backwards. I'm going to do it the other way. And if you've got, we're going to go ahead and delete that. I'm going to go ahead and copy this. And I'm actually going to paste special. I'm going to paste it as the numbers. So there's my numbers. Now I'm going to plot it because I want a position versus time graph, not the other way around. So now you can see my graph here. And what we're doing when we're doing an instantaneous is we're coming in and finding the slope at that point on the graph. So if I were looking at an instantaneous at 6 and I used these 2 points, it's going to be different than if I'm using points that are closer and closer until ultimately I'm at a tangent of the graph. So we want to be able to use our data to be able to calculate that instantaneous velocity and ultimately the instantaneous acceleration. But for what we have here, you've got a homework problem that's going to work an awful lot like this one. So I'm going to go ahead and close that down. I'm going to stop sharing real quick, make sure I'm sharing the right things. So hopefully that helps you with the equation. So one of the things that we've already seen for motion is now I have an equation that looks like this, that x is equal to velocity times time. Because if I have a plot like this, if I look at y equal mx plus b, my y is x, my m, which is my slope, is velocity, time, and then this b would be an initial velocity. So this is if velocity is constant. All right, so we've got an equation here for when velocity is constant. So now I can take and we can define acceleration. Acceleration is defined as a change in velocity with respect to time. Okay, a change in velocity with respect to time. Acceleration is also a vector and velocity is also a vector. So this is going to look like A is equal to my change in velocity over a change in time. And I can rewrite this equation because if we usually start at time as t is equal to 0, I can get acceleration times time is equal to velocity final minus my velocity initial. And typically how we would write this, and you'll see it in your book, is you'll see it written like this. I've got something that looks like this. And now I have another equation of motion. And just like that one, if I make a plot, and as you guys saw that plot with acceleration, if I do velocity versus time, and I get a straight line, this tells me I have a constant acceleration. And my slope, this will be a change in velocity. This is a change in time. My slope are going to be in units of meters per second, which is equal to meters per second squared. And I get this constant velocity. So now if we drop a ball, so we start with my ball at the top, its initial velocity is 0. And we gather some data here. So this is just a ball drop. One of the things we kind of know, because we've had it and we've played with it, is that this ball drop is experiencing an acceleration. It happens to be the acceleration due to gravity. And we're going to use 9.81 meters per second squared. as our acceleration due to gravity. It's pointing downward. Typically, we use down as a negative. So if I have a ball drop, it is experiencing an acceleration. That acceleration is 9.81. Its magnitude is downward. It's down towards the center of the earth. And so I can get an equation that looks like that. Now, if you want to go through all the gory details to derive the equations, you can, but here are our equations of motion. We have velocity final is equal to velocity initial plus the acceleration times time. We have my change in position is equal to my initial velocity times time plus 1/2 acceleration times time squared. And we have velocity final squared is equal to velocity initial squared plus 2 times my acceleration times my change in position. Now, if I look at this one, and we're going to take this one first. If my acceleration is equal to 0, or I have a constant velocity, that equation becomes my change in position is equal to my initial velocity times time. And that looks just like what I had before. So that one gives me this. These only work if acceleration is equal to a constant. So these are a special case, and acceleration is equal to a constant. Now, we've written this with X, but it could be Y, it could be Z, okay? And we can look at it as a variety of different pieces. It could be X, it could be Y, it could be Z. So let's look at a ball toss. So I'm going to be, I don't draw very well. So here's my little person. And I'm going to toss my ball straight up, and it's going to come straight back down. I want to refer you to your example in your text. Because you'll see this problem a lot. So we're going to write our toolbox. So we've got it out here, but we're going to be in the Y direction. So we're going to have our final velocity is equal to our initial velocity plus our acceleration times time. This has variables of V, A, and T. I'm going to do my change in Y because we're in the Y direction, my initial velocity times time plus 1/2 my acceleration times time squared. This has variables. Since that's an initial velocity, it's not a variable. So this has variables of Y, A, and T. And I have velocity final squared is equal to velocity initial squared plus 2 times my acceleration times my change in Y. This has variables of V, A, and Y. Because I always get asked, how do I know which one to use? You'll use which ones are dealing with the variables that you need. We know that I have my acceleration due to gravity here, and it's downward. So our A that we're going to have in here is minus gravity. One of the things that we know is something about the very top. velocity is a vector. So if I am going up, the velocity at the top has got to equal 0 because I'm changing direction. So I get that direction change. So now if we say we're going to toss the ball up with initial velocity of 2 meters per second, we can determine the height and we can determine the time that it takes for it to go up and come back down. So let's figure out the height. I have my, well, I need time here, but I can do this because I know my final velocity. So my final velocity is equal to my initial velocity times time minus 2 times my acceleration due to gravity, 9.81, times my change in position, which in this case is going to equal the height. My final velocity is equal to 0. So I'm going to get velocity squared is equal to 2 times 9.81 times my change in height. So I'm going to get my 2 meters per second squared divided by 2 divided by 9.81 is going to equal my change in height. I'm going to have 4 divided by 2 times 9.81. This gives me that it only went up 2.04 meters. I can use this to find time. Velocity final is equal to my velocity initial minus 9.81 times time. That's equal to 0. So I get velocity initial is equal to 9.81 times time. And I get my initial velocity is 2 meters per second divided by 9.81 meters per second squared. Meters per second can cancel. I end up with seconds on the top. I can find the time that it reaches the top. And that's also happens to be 0.204 seconds. But the total time of flight goes to the top and back. So it's going to be 2 times that. And that'll get me 0.408 seconds. But you have this example in your book that really works through working through all of those to help you out on that one. All right. That should get you started on one-dimensional motion. We'll do more of that on Wednesday, but I want to cover a couple more things because I think people are starting to get brain dead. So let's stop the sharing real quick. And then I'm going to stop the recording real quick.